These high-frequency currents are obtained in a peculiar manner. The method employed was advanced by me about 2 years ago in an experimental lecture before the American Institute of Electrical Engineers. A number of ways, as practiced in the laboratory, of obtaining these currents either from continuous or low-frequency alternating currents is diagrammatically indicated in Fig. 1, which will be later described in detail. The general plan is to charge condensers from a direct or alternate current source, preferably of high tension, and to discharge them disruptively while observing well-known conditions necessary to maintain the oscillations of the current. In view of the general interest taken in high-frequency currents and effects producible by them, it seems to me advisable to dwell at some length upon this method of conversion. In order to give you a clear idea of the action, I will suppose that a continuous current generator is employed, which is often very convenient. It is desirable that the generator should possess such high tension as to be able to break through a small airspace. If this is not the case, then auxiliary means have to be resorted to, some of which will be indicated subsequently. When the condensers are charged to a certain potential, the air, or insulating space, gives way and a disruptive discharge occurs. There is then a sudden rush of current, and generally a large portion of accumulated electrical energy spends itself. The condensers are thereupon quickly charged, and the same process is repeated in more or less rapid succession. To produce such sudden rushes of current, it is necessary to observe certain conditions. If the rate at which the condensers are discharged is the same as that at which they are charged, then, clearly, in the assumed case, the condensers do not come into play. If the rate of discharge be smaller than the rate of charging, then, again, the condensers cannot play an important part. But if, on the contrary, the rate of discharging is greater than that of charging, then a succession of rushes of current is obtained. It is evident that, if the rate at which the energy is dissipated by the discharge is very much greater than the rate of supply to the condensers, the sudden rushes will be comparatively few, with long time intervals between. This always occurs when a condenser of considerable capacity is charged by means of a comparatively small machine. If the rates of supply and dissipation are not widely different, then the rushes of current will be in quicker succession, and this the more nearly equal both the rates are, until limitations incident to each case and depending upon a number of causes are reached. Thus we are able to obtain from a continuous current generator as rapid a succession of discharges as we like. Of course, the higher the tension of the generator, the smaller need be the capacity of the condensers, and for this reason, principally, it is of advantage to employ a generator of very high tension. Besides, such a generator permits the attaining of greater rates of vibration.
The rushes of current may be of the same direction under the conditions before assumed, but most generally there is an oscillation superimposed upon the fundamental vibration of the current. When the conditions are so determined that there are no oscillations, the current impulses are unidirectional, and thus a means is provided of transforming a continuous current of high tension into a direct current of lower tension, which I think may find employment in the arts. This method of conversion is exceedingly interesting, and I was much impressed by its beauty when I first conceived it. It is ideal in certain respects. It involves the employment of no mechanical devices of any kind, and it allows of obtaining currents of any desired frequency from an ordinary circuit, direct or alternating. The frequency of the fundamental discharges, depending on the relative rates of supply and dissipation, can be readily varied within wide limits by simple adjustments of these quantities, and the frequency of the superimposed vibration by the determination of the capacity, self-induction, and resistance of the circuit. The potential of the currents, again, may be raised as high as any insulation is capable of withstanding safely by combining capacity and self-induction, or by induction in a secondary, which need have but comparatively few turns. As the conditions are often such that the intermittence or oscillation does not readily establish itself, especially when a direct current source is employed, it is of advantage to associate an interrupter with the arc, as I have, some time ago, indicated the use of an air blast or magnet or other such device readily at hand. The magnet is employed with special advantage in the conversion of direct currents, as it is then very effective. If the primary source is an alternate current generator, it is desirable, as I have stated on another occasion, that the frequency should be low, and that tile current forming the arc be large in order to render the magnet more effective. A form of such discharger with a magnet which has been found convenient and adopted after some trials, in the conversion of direct currents particularly, is illustrated in Fig. 2. N, S are the pole pieces of a very strong magnet which is excited by a coil, C. The pole pieces are slotted for adjustment and can be fastened in any position by screws S, S, L. The discharge rods DD1 thinned down on the ends in order to allow a closer approach of the magnetic pole pieces pass through the columns of brass BB1 and are fastened in position by screws S2. Springs RR1 and collar CC1 are slipped on the rods, the latter serving to set the points of the rods at a certain suitable distance by means of screws S3 and the former to draw the points apart. When it is desired to start the arc, one of the large rubber handles HH1 is tapped quickly with the hand, whereby the points of the rods are brought in contact but are instantly separated by the springs RR1. Such an arrangement has been found to be often necessary, namely in cases when the EMFF was not large enough to cause the discharge to break through the gap, and also when it was desirable to avoid short-circuiting of the generator by the metallic contact of the rods. The rapidity of the interruptions of the current with a magnet depends on the intensity of the magnetic field and on the potential difference at the end of the arc. The interruptions are generally in such quick succession as to produce a musical sound. Years ago, it was observed that when a powerful induction coil is discharged between the poles of a strong magnet, the discharge produces a loud noise not unlike a small pistol shot. It was vaguely stated that the spark was intensified by the presence of the magnetic field. It is now clear that the discharge current, flowing for some time, was interrupted a great number of times by the magnet, thus producing the sound. The phenomenon is especially marked when the field circuit of a large magnet or dynamo is broken in a powerful magnetic field. When the current through the gap is comparatively large, it is of advantage to slip on the points of the discharge rod's pieces of very hard carbon and let the arc play between the carbon pieces. This preserves the rods, and besides has the advantage of keeping the airspace hotter, as the heat is not conducted away as quickly through the carbons, and the result is that a smaller EMFF in the arc gap is required to maintain a succession of discharges. Another form of discharger, which may be employed with advantage in some cases, is illustrated in Fig. 3. In this form, the discharge rods DD1 pass through perforations in a wooden box B, which is thickly coated with mica on the inside, as indicated by the heavy lines. The perforations are provided with mica tubes MM1 of some thickness, which are preferably not in contact with the rods DD1. The box has a cover C, which is a little larger, and descends on the outside of the box. The spark gap is warmed by a small lamp L contained in the box. A plate P above the lamp allows the draft to pass only through the chimney A of the lamp, the air entering through holes OO in or near the bottom of the box and following the path indicated by the arrows. When the discharger is in operation, the door of the box is closed so that the light of the arc is not visible outside. It is desirable to exclude the light as perfectly as possible, as it interferes with some experiments. This form of discharger is simple and very effective when properly manipulated. The air being warmed to a certain temperature has its insulating power impaired, it becomes dielectrically weak, as it were, and the consequence is that the arc can be established at much greater distance. The arc should, of course, be sufficiently insulating to allow the discharge to pass through the gap disruptively. The arc formed under such conditions, when long, may be made extremely sensitive, and the wheel, draft through the lamp chimney A, is quite sufficient to produce rapid interruptions. The adjustment is made by regulating the temperature and velocity of the draft. Instead of using the lamp, it answers the purpose to provide for a draft of warm air in other ways. A very simple way which has been practiced is to enclose the arc in a long vertical tube with plates on the top and bottom for regulating the temperature and velocity of the air current. Some provision had to be made for deadening the sound. The air may be rendered dielectrically weak also by rarefaction. Dischargers of this kind have likewise been used by me in connection with a magnet. A large tube is for this purpose provided with heavy electrodes of carbon or metal, between which the discharge is made to pass, the tube being placed in a powerful magnetic field. The exhaustion of the tube is carried to a point at which the discharge breaks through easily, but the pressure should be more than 75 mm, at which the ordinary thread discharge occurs. In another form of discharger, combining the features before mentioned, the discharge was made to pass between two adjustable magnetic pole pieces, the space between them being kept at an elevated temperature.
We will move on to the next section shortly, but before that I want to share something that might be very useful for you. Inspired by successful YouTube creators making fortunes from their channels, then Tube Mastery and Monetization course from Matt Barr can help you get real results on YouTube with personal attention from him and his content team. Lots of people have already succeeded with their channels thanks to him. He also has Tube Magic software tool that can help you accomplish more when it comes to making content.
Links in the description. I've also prepared a video for you that talks more about that, as well as solutions to challenges like online security, financial progress, and additional creativity. There, we'll explore these topics with respect and care for you. I warmly invite you to watch this video when you get a chance. Either way, your support is the current that powers this channel. And now back to the show.
It should be remarked here that when such, or interrupting devices of any kind, are used and the currents are passed through the primary of a disruptive discharge coil, it is not, as a rule, of advantage to produce a number of interruptions of the current per second greater than the natural frequency of vibration of the dynamo supply circuit, which is ordinarily small. It should also be pointed out here that while the devices mentioned in connection with the disruptive discharge are advantageous under certain conditions, they may be sometimes a source of trouble, as they produce intermittences and other irregularities in the vibration which it would be very desirable to overcome. There is, I regret to say, in this beautiful method of conversion, a defect which fortunately is not vital, and which I have been gradually overcoming. I will best call attention to this defect and indicate a fruitful line of work by comparing the electrical process with its mechanical analog. The process may be illustrated in this manner. Imagine a tank with a wide opening at the bottom, which is kept closed by spring pressure, but so that it snaps off suddenly when the liquid in the tank has reached a certain height. Let the fluid be supplied to the tank by means of a pipe, feeding at a certain rate. When the critical height of the liquid is reached, the spring gives way, and the bottom of the tank drops out. Instantly the liquid falls through the wide opening, and the spring, reasserting itself, closes the bottom again. The tank is now filled, and after a certain time interval the same process is repeated. It is clear that if the pipe feeds the fluid quicker than the bottom outlet is capable of letting it pass through, the bottom will remain off, and the tank will still overflow. If the rates of supply are exactly equal, then the bottom lid will remain partially open, and no vibration of the same and of the liquid column will generally occur, though it might, if started by some means. But if the inlet pipe does not feed the fluid fast enough for the outlet, then there will be always vibration. Again, in such case, each time the bottom flaps up or down, the spring and the liquid column, if the pliability of the spring and the inertia of the moving parts are properly chosen, will perform independent vibrations. In this analog, the fluid may be likened to electricity or electrical energy, the tank to the condenser, the spring to the dielectric, and the pipe to the conductor through which electricity is supplied to the condenser. To make this analogy quite complete, it is necessary to make the assumption that the bottom, each time it gives way, is knocked violently against a non-elastic stop, this iron-packed involving some loss of energy, and that, besides, some dissipation of energy results due to frictional losses. In the preceding analog, the liquid is supposed to be under a steady pressure. If the presence of the fluid be assumed to vary rhythmically, this may be taken as corresponding to the case of an alternating current. The process is then not quite as simple to consider, but the action is the same in principle. It is desirable, in order to maintain the vibration economically, to reduce the impact and frictional losses as much as possible. As regards the latter, which in the electrical analog correspond to the losses due to the resistance of the circuits, it is impossible to obviate them entirely, but they can be reduced to a minimum by a proper selection of the dimensions of the circuits and by the employment of thin conductors in the form of strands. But the loss of energy caused by the first breaking through of the dielectric, which in the above example corresponds to the violent knock of the bottom against the inelastic stop, would be more important to overcome. At the moment of the breaking through, the airspace has a very high resistance, which is probably reduced to a very small value when the current has reached some strength and the space is brought to a high temperature. It would materially diminish the loss of energy if the space were always kept at an extremely high temperature, but then there would be no disruptive break. By warming the space moderately, by means of a lamp or otherwise, the economy as far as the arc is concerned is sensibly increased. But the magnet or other interrupting device does not diminish the loss in the arc. Likewise, a jet of air only facilitates the carrying off of the energy. Air, or a gas in general, behaves curiously in this respect. When two bodies charged to a very high potential discharge disruptively through an airspace, any amount of energy may be carried off by the air. This energy is evidently dissipated by bodily carriers in impact and collisional losses of the molecules. The exchange of the molecules in the space occurs with inconceivable rapidity. A powerful discharge taking place between two electrodes, they may remain entirely cool, and yet the loss in the air may represent any amount of energy. It is perfectly practicable, with very great potential differences in the gap, to dissipate several horsepower in the arc of the discharge without even noticing a small increase in the temperature of the electrodes. All the frictional losses occur then practically in the air. If the exchange of the air molecules is prevented, as by enclosing the air hermetically, the mass inside of the vessel is brought quickly to a high temperature, even with a very small discharge. It is difficult to estimate how much of the energy is lost in sound waves, audible or not, in a powerful discharge. When the currents through the gap are large, the electrodes may become rapidly heated, but this is not a reliable measure of the energy wasted in the arc, as the loss through the gap itself may be comparatively small. The air or a gas in general is at ordinary pressure at least, clearly not the best medium through which a disruptive discharge should occur. Air or other gas under great pressure is of course a much more suitable medium for the discharge gap. I have carried on long-continued experiments in this direction, unfortunately less practicable on account of the difficulties and expense in getting air under great pressure. But even if the medium in the discharge space is solid or liquid, still the same losses take place, though they are generally smaller, for just as soon as the arc is established, the solid or liquid is volatilized. Indeed, here is no body known which would not be disintegrated by the arc, and it is an open question among scientific men whether an arc discharge could occur at all in the air itself without the particles of the electrodes being torn off. When the current through the gap is very small and the arc very long, I believe that a relatively considerable amount of heat is taken up in the disintegration of the electrodes, which partially on this account may remain quite cold. The ideal medium for a discharge gap should only crack, and the ideal electrode should be of some material which cannot be disintegrated. With small currents through the gap, it is best to employ aluminum, but not when the currents are large. The disruptive break in the air, or more or less in any ordinary medium, is not of the nature of a crack, but it is rather comparable to the piercing of innumerable bullets through a mass offering great frictional resistances to the motion of the bullets, this involving considerable loss of energy. A medium which would merely crack when strained electrostatically, and this possibly might be the case with a perfect vacuum, that is, pure ether, would involve a very small loss in the gap, so small as to be entirely negligible, at least theoretically, because a crack may be produced by an infinitely small displacement. In exhausting an oblong bulb, provided with two aluminum terminals, with the greatest care, I have succeeded in producing such a vacuum that the secondary discharge of a disruptive discharge coil would break disruptively through the bulb in the form of fine spark streams. The curious point was that the discharge would completely ignore the terminals and start far behind the two aluminum plates which served as electrodes. This extraordinary high vacuum could only be maintained for a very short while. To return to the ideal medium, think, for the sake of illustration, of a piece of glass or similar body clamped in a vise, and the latter tightened more and more. At a certain point, a minute increase of the pressure will cause the glass to crack. The loss of energy involved in splitting the glass may be practically nothing, for though the force is great, the displacement need be but extremely small. Now imagine that the glass would possess the property of closing again perfectly, the crack upon a minute diminution of the pressure. This is the way the dielectric in the discharge space should behave, but inasmuch as there would be always some loss in the gap, the medium, which should be continuous, should exchange through the gap at a rapid rate. In the preceding example, the glass being perfectly closed, it would mean that the dielectric in the discharge space possesses a great insulating power. The glass being cracked, it would signify that the medium in the space is a good conductor. The dielectric should vary enormously in resistance by minute variations of the EMF F across the discharge space. This condition is attained, but in an extremely imperfect manner, by warming the air space to A. certain critical temperature, dependent on the EMF across the gap, or by otherwise impairing the insulating power of the air. But as a matter of fact, the air does never break down disruptively, if this term be rigorously interpreted, for before the sudden rush of the current occurs, there is always a weak current preceding it, which rises first gradually and then with comparative suddenness. That is the reason why the rate of change is very much greater when glass, for instance, is broken through than when the break takes place through an air space of equivalent dielectric strength. As a medium for the discharge space, a solid or even a liquid would be preferable therefore. It is somewhat difficult to conceive of a solid body which would possess the property of closing instantly after it has been cracked. But a liquid, especially under great pressure, behaves practically like a solid, while it possesses the property of closing the crack. Hence it was thought that a liquid insulator might be more suitable as a dielectric than air. Following out this idea, a number of different forms of dischargers in which a variety of such insulators, sometimes under great pressure, were employed, have been experimented upon. It is thought sufficient to dwell in a few words upon one of the forms experimented upon. One of these dischargers is
We will move on to the next section shortly, but before that I want to share something that might be very useful for you. Inspired by successful YouTube creators making fortunes from their channels, then Tube Mastery and Monetization course from Matt Barr can help you get real results on YouTube with personal attention from him and his content team. Lots of people have already succeeded with their channels thanks to him. He also has Tube Magic software tool that can help you accomplish more when it comes to making content. Links in the description. I've also prepared a video for you that talks more about that, as well as solutions to challenges like online security, financial progress, and additional creativity. There, we'll explore these topics with respect and care for you. I warmly invite you to watch this video when you get a chance. Either way, your support is the current that powers this channel. And now back to the show.
illustrated in figs 4A and 4B, a hollow metal pulley, P fig. 4A was fastened upon an arbor A which by suitable means was rotated at a considerable speed. On the inside of the pulley, but disconnected from the same, was supported a thin disc, H, which is shown thick for the sake of clearness, of hard rubber in which there were embedded two metal segments, SS, with metallic extensions, EE, into which were screwed, conducting terminals, TT, covered with thick tubes of hard rubber, TT. The rubber disc, B, with its metallic segments, SS, was finished in a lathe, and its entire surface highly polished so as to offer the smallest possible frictional resistance to the motion through a fluid. In the hollow of the pulley an insulating liquid, such as a thin oil, was poured, so as to reach very nearly to the opening left in the flange F, which was screwed tightly on the front side of the pulley. The terminals TT were connected to the opposite coatings of a battery of condensers so that the discharge occurred through the liquid. When the pulley was rotated, the liquid was forced against the rim of the pulley and considerable fluid pressure resulted. In this simple way, the discharge gap was filled with a medium which behaved practically like a solid, which possessed the duality of closing instantly upon the occurrence of the break, and which moreover was circulating through the gap at a rapid rate. Very powerful effects were produced by discharges of this kind with liquid interrupters, of which a number of different forms were made. It was found that, as expected, a longer spark for a given length of wire was obtainable in this way than by using air as an interrupting device. Generally the speed, and therefore also the fluid pressure, was limited by reason of the fluid friction, in the form of discharger described, but the practically obtainable speed was more than sufficient to produce a number of breaks suitable for the circuits ordinarily used. In such instances the metal pulley P was provided with a few projections inwardly, and a definite number of breaks was then produced which could be computed from the speed of rotation of the pulley. Experiments were also carried on with liquids of different insulating power with the view of reducing the loss in the arc. When an insulating liquid is moderately warmed, the loss in the arc is diminished. A point of some importance was noted in experiments with various discharges of this kind. It was found, for instance, that whereas the conditions maintained in these forms were favorable for the production of a great spark length, the current so obtained was not best suited to the production of light effects. Experience undoubtedly has shown that for such purposes A harmonic rise and fall of the potential is preferable. Be it that a solid is rendered incandescent or phosphorescent, or be it that energy is transmitted by condenser coating through the glass, it is quite certain that a harmonically rising and falling potential produces less destructive action, and that the vacuum is more permanently maintained. This would be easily explained if it were ascertained that the process going on in an exhausted vessel is of an electrolytic nature. In the diagrammatical sketch, Fig. 1, which has been already referred to, the cases which are most likely to be met with in practice are illustrated. One has at his disposal either direct or alternating currents from a supply station. It is convenient for an experimenter in an isolated laboratory to employ a machine G, such as illustrated, capable of giving both kinds of currents. In such case, it is also preferable to use a machine with multiple circuits, as in many experiments it is useful and convenient to have at one's disposal currents of different phases. In the sketch, D represents the direct and A the alternating circuit. In each of these, 3 branch circuits are shown, all of which are provided with double-line switches SSSSSS. Consider first the direct current conversion. La represents the simplest case. If the EMF of the generator is sufficient to break through a small air space, at least when the latter is warmed or otherwise rendered poorly insulating, there is no difficulty in maintaining a vibration with fair economy by judicious adjustment of the capacity, self-induction, and resistance of the circuit. L containing the devices LLM. The Magnet-NS can be in this case advantageously combined with the airspace, the discharger DD, with the magnet may be placed either way, as indicated by the full or by the dotted lines. The circuit La, with the connections and devices, is supposed to possess dimensions such as are suitable for the maintenance of a vibration, but usually the EMF on the circuit or branch La will be something like a 100 volts or so, and in this case it is not sufficient to break through the gap. Many different means may be used to remedy this by raising the EMF across the gap. The simplest is probably to insert a large self-induction coil in series with the circuit L, when the arc is established, as by the discharger illustrated in Fig. 2. The magnet blows the arc out the instant it is formed. Now the extra current of the break, being of high EMF, breaks through the gap, and a path of low resistance for the dynamo current being again provided, there is a sudden rush of current from the dynamo upon the weakening or subsidence of the extra current. This process is repeated in rapid succession, and in this manner I have maintained oscillation with as low as 50 volts, or even less, across the gap. But conversion on this plan is not to be recommended on account of the too heavy currents through the gap and consequent heating of the electrodes. Besides, the frequencies obtained in this way are low owing to the high self-induction necessarily associated with the circuit. It is very desirable to have the EMFF as high as possible, first, in order to increase the economy of the conversion, and secondly, to obtain high frequencies. The difference of potential in this electric oscillation is, of course, the equivalent of the stretching force in the mechanical vibration of the spring. To obtain very rapid vibration in a circuit of some inertia, a great stretching force or difference of potential is necessary. Incidentally, when the EMF is very great, the condenser which is usually employed in connection with the circuit need but have a small capacity, and many other advantages are gained. With a view of raising the EMF to a many times greater value than obtainable from ordinary distribution circuits, a rotating transformer G is used, as indicated at IA, Fig. Fig. 1, or else a separate high potential machine is driven by means of a motor operated from the generator G. The latter plan is in fact preferable, as changes are easier made. The connections from the high-tension winding are quite similar to those in branch law, with the exception that a condenser C, which should be adjustable, is connected to the high-tension circuit. Usually, also, an adjustable self-induction coil in series with the circuit has been employed in these experiments. When the tension of the currents is very high, the magnet ordinarily used in connection with the discharger is of comparatively small value, as it is quite easy to adjust the dimensions of the circuit so that oscillation is maintained. The employment of a steady EMF in the high-frequency conversion affords some advantages over the employment of alternating EMF, as the adjustments are much simpler and the action can be easier controlled. But unfortunately, one is limited by the obtainable potential difference. The winding also breaks down easily in consequence of the sparks which form between the sections of the armature or commutator when a vigorous oscillation takes place. Besides, these transformers are expensive to build. It has been found by experience that it is best to follow the plan illustrated at MET. In this arrangement, a rotating transformer G is employed to convert the low-tension direct currents into low-frequency alternating currents, preferably also of small tension. The tension of the currents is then raised in a stationary transformer, T. The secondary S of this transformer is connected to an adjustable condenser, C, which discharges through the gap or discharger DD, placed in either of the ways indicated, through the primary P of a disruptor discharge coil, the high-frequency current being obtained from the secondary S of this coil, as described on previous occasions. This will undoubtedly be found the cheapest and most convenient way of converting direct currents. The three branches of the circuit, A, represent the usual cases met in practice when alternating currents are converted. In Fig. 1b, a condenser, C, generally of large capacity, is connected to the circuit L, containing the devices L, L, M, M. The devices MM are supposed to be of high self-induction, so as to bring the frequency of the circuit more or less to that of the dynamo. In this instance, the discharger DD should best have a number of makes and breaks per second equal to twice the frequency of the dynamo. If not so, then it should have at least a number equal to a multiple or even fraction of the dynamo frequency. It should be observed, referring to IB, that the conversion to a high potential is also effected when the discharger DD, which is shown in the sketch, is omitted. But the effects which are produced by currents which rise instantly to high values, as in a disruptive discharge, are entirely different from those produced by dynamo currents which rise and fall harmonically. So, for instance, there might be in a given case a number of makes and breaks at DD equal to just twice the frequency of the dynamo, or in other words, there may be the same number of fundamental oscillations as would be produced without the discharge gap, and there might even not be any quicker superimposed vibration, yet the differences of potential at the various points of the circuit, the impedance, and other phenomena, dependent upon the rate of change, will bear no similarity in the two cases. Thus, when working with currents discharging disruptively, the element chiefly to be considered is not the frequency, as a student might be apt to believe, but the rate of change per unit of time. With low frequencies, in a certain measure, the same effects may be obtained as with high frequencies, provided the rate of change is sufficiently great. So if a low-frequency current is raised to a potential of, say, 75,000 volts, and the high-tension current passed through a series of high-resistance lamp filaments, the importance of the rarefied gas surrounding the filament is clearly noted, as will be seen later. Or, if a low-frequency current of several thousand amperes is passed through a metal bar, striking phenomena of impedance are observed, just as with currents of high frequencies. But it is, of course, evident that with low-frequency currents it is impossible to obtain such rates of change per unit of time as with high frequencies, hence the effects produced by the latter are much more prominent. It is deemed advisable to make the preceding remarks, inasmuch as many more recently described effects have been unwittingly identified with high frequencies. Frequency alone in reality does not mean anything, except when an undisturbed harmonic oscillation is considered. In the branch 3b, a similar disposition to that in 1b is illustrated, with the difference that the currents discharging through the gap DD are used to induce currents in the secondary S of a transformer T. In such case, the secondary should be provided with an adjustable condenser for the purpose of tuning it to the primary. 2b illustrates a plan of alternate current high-frequency conversion which is most frequently used, and which is found to be most convenient. This plan has been dwelt upon in detail on previous occasions, and need not be described here. Some of these results were obtained by the use of a high-frequency alternator. A description of such machines will be found in my original paper before the American Institute of Electrical Engineers, and in periodicals of that period, notably in the Electrical Engineer of March 18, 1891. I will now proceed with the experiments.
Thanks for watching to the end of this video. If you want more content like this, there is a playlist that should be popping up right now. Stay tuned for more. I've also made this free video for you with solutions for creativity, financial strength, and online security. I hope you'll enjoy this offer as well as all the others featured on my channel. And that concludes this video. Thanks for watching, and until next time, this is Hermolau Tube. My name is Konstantin, reminding you that your interest is the current that powers this channel.